We will move on now to the first part of our agenda, and that's to look at the internet from a statistical point of view. And to do that, I'd like to invite Stephen Stuart to come and chair this session. Stephen, I'm not going to try to give a précis of your background. You're welcome to take a few minutes to do that, but I will tell you that Stephen has been a bastion of development in my world anyway, on the IPv6 side, on measurement, and other activities that are so critical to the net. So I appreciate very much, Stephen, you're taking the time to join us this morning. I'll turn this over to you.
Thanks. Thanks, and greetings to everyone. We had planned a statistical view of the internet, starting with the very large, and then getting down to the very small. Alan, I believe, was going to handle our view of the very large.
Well, thanks for having me here. My name is Alan Mauldin. I work with Telegeography Research, which is a market research company focused on global telecommunications based in Washington, D.C., although I am based in Bratislava, Slovakia. I'm going to talk about the internet at its core basic level globally, which is the undersea cable system largely, as well as some of the capacity available internationally around the world. So I have a few slides I want to run through that touch on some of these issues. The first slide here is a map showing the current undersea cables around the world. They're scaled by the capacity, the lit capacity, how much has been equipped and is currently active on the systems. So you can see between the US and Europe, it's about 12 to 13 high-capacity systems in place. Across the Pacific, about 8. Several to South America, and in the intra-Asian area, roughly between Singapore and Japan, we have quite a few systems, all with very high capacity. This is changing quite rapidly, actually, the way this map looks. In the next year, you're going to see new cables to Greenland, to East Africa even, some to islands in the South Pacific. So you're really seeing an expansion of the cable infrastructure to some very far-flung places. At the same time, you're seeing new cables on many of these routes that are already in place. You're seeing 5 new cables between Europe and the Middle East. We had 1 across the Pacific last year. We're going to have 2 to 3 more across the Pacific in the next 18 months as well. So it's clearly evolving rapidly. There's a bit of a cable boom right now underway. There's about 16 new cables coming in service just in this year alone.
What's the typical capacity of the cable in terms of fibers these days?
Generally, what we're seeing is 4 fiber pairs. You can do as many as 8, but it's more costly. So carriers are going for a 4 to 5 fiber pair system usually, and it can handle usually 96 to 128 waves, 10 gig waves.
That number changes over time.
It can change over time. It's possible, but right now most of the cables that are currently in place, they can't do more than 128 waves per fiber pair. Yeah, exactly.
I'm sorry to interrupt for just 1 second. I'm trying to figure out whether the people who are watching this are going to hear questions without benefit of a microphone. What's the situation? They won't? All right, so we need a microphone, a handheld. Okay, so yeah, if we're going to do Q&A, we need to use microphones. Okay, thanks.
Okay. Uh-oh. This was a nice image showing the capacity growth over time of
it is changing rapidly.
It's an envelope. You have to open it up to see what's inside. What you would have seen here, I'm not sure why this didn't work, is
this is a PC Mac problem. Is that right?
I use a Mac to make this, so.
Wow, weird. All right. So much for standard.
Right. So this was showing on the version that I sent, which did work actually, was the increase in lit capacity over time for the past 5 years. 7 years. So what we've been seeing actually is not an envelope, but a relatively slow growth of capacity between 2002 and 2005. There wasn't much need for new capacity because there was so much capacity of the cables that was installed during the telecom boom of the early 2000s that there wasn't any need for new capacity. But in the past few years, it's done this. Last year alone across the Pacific, lit capacity grew 121%. That's a result of one new cable, but also several cables were upgraded. So they were either had new fiber pairs lit on them or had more waves added to existing lit fiber pairs. So hopefully the next one's going to work. I'm gonna hold my breath. So this is another image that shows the same 5 routes, major global routes that were on the previous slide that didn't come through. But so this is the lit capacity versus the potential capacity of installed cables at the end of this past year. So you can see roughly how much is lit. Across the Atlantic, it's 25%. Pacific is 30%. The one that might seem worrisome is the Europe to Asia route, which are cables that go from Europe through Asia down through the Red Sea across the Middle East. They are quite utilized. The good news is there's about 5 new cables that are going to come online in the next 12 months, which will add the potential for about I think 18 terabits extra. So right now we're at a total of I think 3 terabits potential on those cables. So clearly, the Europe to Asia route is going to get plenty of new capacity in the next few years.
How much does it cost to light a wave, say, transatlantic?
It's a very important question because
Repeat the question for the audience.
the question was how much does it cost to light a wavelength across the Atlantic? I think in card cost, for the wavelength card cost, it's about $200,000. That's been coming down a lot. I think if you're buying in bulk, you can get it down to $100,000 for a pair on either end. That doesn't include the cost of the backhaul from the station into the city pop. But the other point here is even though it seems that it's relatively underutilized, with only 25% of the Atlantic is lit of what's potential, even though the potential is 39 terabits. At current growth rates, this could be exhausted by 2014, we think, which means the time to start considering building a new cable could be coming up rather soon. Because once capacity is gone, you don't need one cable, you need several cables. So the last slide I wanted to touch on here was just showing this is data we have on public internet capacity, country to country. This is the aggregate totals of the various backbone operators, just the international links between various countries. And it's only showing the routes that are over 30 gigabits in aggregate. So obviously the internet does go to Africa and the Middle East, just not it's not shown right here on the data set. What's important about the way this looks now is I think everybody knows the internet's becoming more regionally focused in the way traffic is routed and how capacity is growing. But if you look at how the continents are linked, it's still largely through the United States. South America goes all through the United States to get to anywhere in the rest of the world. Asia largely is still going through the U.S. to get anywhere. There is a growing amount of capacity between Europe and Asia directly, both subsea and terrestrially across Russia, but it's really small compared to what is in place across the Pacific, and it's much more expensive as well right now to go on cables via the Middle East or across Russia. That's all I wanted to touch on right now. If there's any questions.
So can we get the microphones here so
Yeah.
save you the trouble of repeating?
Thank you. So 2 questions. What is the relative cost of terrestrial versus undersea cables? And the other is, are you seeing any change due to the economic changes in global economic conditions in this segment in cables?
I mean, in terms of the cost, it's going to vary by the region, obviously, and how much capacity is installed. So it's really hard for me to state the differences. A cable going across Russia, the cost of that's far more expensive to maintain and operate than one going across the United States, for instance. The price is probably 10 times as high across Russia than going across the United States. The question was about the impact of the current economic crisis on existing cable projects and cable builds. So far, we've not seen any projects being canceled at all. Most cables are still being built. I think if there's a new project that's coming along, it could have a hard time getting funding. But just in the past 3 months, we've seen, I think, 3 projects announced, some pretty big projects that were announced and had contracts signed. So clearly, I mean, these are long-term investments that are being made. So there was a new cable announced that goes up the coast of West Africa that's going to be going into service in 2011. It's a $600 million cable that was announced just last month. So the money is still coming in to the cable sector. Yes.
How much of the capacity that you displayed is basically raw bit carrying capacity, irrespective of protocol, versus the internet? Have you parsed it in this presentation? And the second question, which is a perennial one, is how much of this is sort of unlit purposely by some of the owners of the cable systems to drive up demand?
Right. What we're showing here is just the layer 3 the layer 3 internet capacity, but the previous slides are showing raw capacity, the potential capacity of the system. And I can just go back and show this. So this is showing the potential capacity in red here in this slide. So yeah, that is not being lit or currently utilized. But I don't think cable owners are withholding it for any reason. They've been adding capacity rapidly the past few years. So I don't think there's any plans right now to keep fiber pairs unlit. They're trying to serve demand as fast as they can.
So what percentage of this is IP traffic versus non-IP traffic?
I don't have that. No. Yes.
So for the systems that are going in now, as I understand it, these are usually done by consortiums. And who is active in these consortia? Who is actually paying for this stuff?
That's a good question. We are still seeing some activity among consortiums, but also seeing private operators still in some parts of the world. Private cables go in smaller markets where there's an opportunity to really make a large profit. Usually, it's a higher risk as well. The consortiums that we're seeing now are smaller consortiums, such as the one that Google's involved with across the Pacific, the Unity project. It's, I believe, 7 members. So you're still seeing the traditional telcos largely leading a lot of the investment. So you're seeing Verizon, AT&T still being very active, as well as carriers in India and the Middle East. A lot of the new builds there. So Saudi Telecom Egypt, Tata Communications, Reliance out of India as well are building a lot of cables.
Are there any other major non-traditional participants?
No. Google was really the first one that I can think of to take a very large role in cable ownership and in building the cable. You have non-carrier entities as large owners of capacity on cables, definitely. But in terms of being at the forefront of trying to build and design the system and invest in it, it's still largely the carriers.
So I'd like to switch over to Tom's presentation now, so we have some time for questions at the end. And having wreaked havoc on this whole setup once, here we go again.
I had correctly interpreted the order in which you were going to do it.
So we're now we're going from the very macroscopic. Now we're going to talk about the network that's been built out of this stuff.
Okay, I'm going to show you some data on packet.
Tom, you want to a little bit about yourself? Just so because I didn't introduce everybody.
Oh, that's okay. I'm Tom Leighton. I'm the chief scientist and co-founder of Akamai Technologies and a professor of mathematics at MIT. And I'm going to show you some data on packet loss, latency, and throughput at various points in the internet. So we'll start with some packet loss and latency. And the data I'm going to show you here is at 2 nines. That means it's sampling at the worst 1% of performance. And the idea here is that, well, basically, if you take averages, things look pretty good. You know, modular getting into China, but otherwise, things are pretty good. And people like to think of their applications running in a data center at 5 nines. And the internet is far from that. And to sort of get a feel for that, this data is at 2 nines, so the 99th percentile of performance. And it's sort of what you'd expect. You know, if you're going in the United States, you know, things aren't so bad. So if you're going from San Francisco to Chicago, you know, you can do 60 milliseconds. This is data taken across a 2-week interval in the internet. Nothing dramatic happened during that time. At 2 nines, you got 6% packet loss. And you don't really have anything that you would call, you know, hours of degraded performance. You know, things are pretty good. Now, I'm going to show you data on internet. That's just, you know, doing a ping from, you know, between the pairs of points in the internet. Akamai has an overlay on top of the internet, and that will show you what is capable with the hardware that's there. Okay, now you don't get access to all the wires. Your packets follow paths determined by BGP and what the networks, you know, want the routes to be taken. And we have, since we have our servers in 900 networks, we can sort of control how we map our data through the internet. And this says that the best you could hope to do, you know, at 2 nines is 51 milliseconds. So not a big difference within the U.S.
Are these one-way latencies or round-trip time?
This is round-trip time, ping time. So say you go down to South America and you start to see some differences. Packet loss, not bad. At 2 nines, you still have no packet loss, pretty good. But you can start to see that your latencies are a lot higher than what you might think of as optimal going to South America. So you're paying 300 milliseconds versus maybe some kind of notion of optimal at 180. And of course, if you were to go into China, which is maybe one of the worst places to try to go, packet loss only at 16% is pretty nasty at 2 nines. You have a hard time doing 2 nines into China, but you see dramatic latencies there, very bad. And look at the hours of degraded performance. Basically, every workday in China, during the whole workday, it's very poor behavior, performance going into China.
Do we know why?
Yeah, there's a couple of reasons. It's when traffic increases, and there's very poor connectivity between the major carriers, you know, CNC and China Telecom. And of course, there's the great firewall, you know, at the perimeter of the country, filtering traffic coming in. And as traffic goes up, it becomes less effective, and things get really slow. Yeah.
You have 323 hours out of what period of time?
2-week period.
So 2 weeks is 336, right?
Yeah, it's pretty bad. In fact, there's degraded and there's unusable. Unusable is, in a subjective measure, is close to 10 hours a day during the weekdays.
Are you able to tell us which 13 hours are the right hours?
We probably could. You know, it's not the hours you want to use, probably.
What's your definition of degraded?
Degraded is based on packet loss and latency compared to optimal. And there's an absolute amount of latency versus and a percentage of latency. So if you go from 2 milliseconds to 4 milliseconds, that's a big percentage, but it's non-material. And then packet loss is thrown in as well. And it's somewhat of a subjective, you know, measure that if you're running an application across that link, it would be degraded means you start noticing it slow and not so easy. And there's an unusable measure, which I didn't include here, which means it really is unusable. You shouldn't expect your employees to be doing it.
So these are ICMP echo request, ICMP echo response type measures?
That's correct.
And the same for Akamai also? Is that just routed through your fabric instead?
That's correct.
And do you prioritize ICMP traffic differently from the rest of the traffic at all?
No.
You don't.
So in
it's
fact,
equal. So, okay. Do you know about the relative? I mean, do you have statistics on the relative difference of handling for priority for ICMP versus other traffic?
I don't know if we do or not. So I don't know the answers on that.
Okay.
In that statistic, are you going through the Great Firewall? Or is that beyond?
This is going through the Great Firewall because we have to leave the country. So we're not doing any caching, none of the stuff you would think of Akamai as doing. This is just transport layer, and it's tunneling. In this case, the Akamai scores would be tunneling through other Akamai servers and other networks along the way. And typically out of China, you're probably making 2 stopovers on the way through Akamai servers. Now, if you look at Europe, it's a similar story, but because the geographies are closer within Europe, you know, things are actually pretty good. You know, you could go London to Amsterdam, and you see here's an example where you get a big difference in percentage of latency, but it's not material because, you know, it's only talking 8 milliseconds. You have to be doing a lot of round trips before that matters. You know, a less nice place would be going London, Milan. You know, you're looking at 6% packet loss at 2 nines, not so bad. You see no degraded hours effectively, and the latency difference is percentage-wise a lot, but not necessarily material. If you go to Asia, inside Asia, things are pretty nasty. Tokyo to Singapore, whoops, that went. Let's see if I can get that to come up.
The color coding is?
Green is better than red, and yellow's in between in terms of performance. So Singapore would be a good location. And now here you got 2 nines at 12% packet loss. And if you, in this case, you go to Seoul. Here you have large latencies, not so bad packet loss. Down to Sydney, sort of in between. Again, big latency differences, not so much in packet loss. So Asia is not so nice to be going, city to city in Asia, and partly that's because the geography is spread across. That was all that data is from a normal 2-week period. These are some events that occurred in the internet where things are not so normal across. This is a little over about a week and a half period where we had the earthquake in Taiwan. A lot of those cables we just saw had disruptions. This is data taken to run an application, and it's being tested from several points in Asia back into the United States, the application running in the US. The red line is what was happening on the internet. The green line is the same application that's running on using this overlay network that Akamai runs for its customers. And you can see, of course, when the earthquake hits, an application was taking a few seconds to run, goes to over a minute. There's an 8-hour period where it totally fails. And of course, many sites were just completely down. Many transactions could not be run for even longer than 8 hours when that earthquake hit. And then between Taiwan and the US. This is several points in Asia, including Taiwan. But there were several locations in Asia that were impacted because the cables, of course, we just saw go into one location and fan out. And I got away from the mic here. Sorry. And then you see the problem, and you see, as cables get fixed, things get better. But it was nasty for a while. This is the same event, and now we're looking at packet loss. Wow. And you can see that the packet loss quickly spikes to over 60%. Something happens to make things better a day later, and it's down to 50%. And then maybe you can see the events when cables are being fixed. And life is getting better, but you're looking at a 2-week period where you're still over 10% packet loss. And now this is not 2 nines anymore. This is just average behavior. So you can see, the fragility of the system. If you knock out a bunch of the cables, the internet does not perform very well. We saw the same thing with the Mideast cable cut. This again is showing latency in milliseconds in this case, something that was a baseline of 200 milliseconds quickly spiking to over 500 milliseconds, and then as repairs happen, slowly getting back to normal. And this is showing a 2-week period. Green again is Akamai. There is capability to get bandwidth out if you had control of all the infrastructure. So it's not an infrastructure problem as much as it is how it's used, the routing protocols. Here's packet loss after the Mideast cable cut. And this is going from the US into, I think it's into India through that territory, into the Middle East. Now I'm going to shift gears a little bit and talk about bandwidth throughput. And this is measured from real data as we're delivering movies and software downloads to end users. And what we're measuring here is an average over all IPs that we see. Now, IPs are very loosely correlated with end users. Many end users can be behind the same IP, the firewall here. You can have dynamic IP space. So one user might see a lot of IPs. So it's not a one-to-one correlation with end users, but it's an approximation. And this is showing the actual delivery rate averaged over IPs that we see. And we see pretty much every IP in the internet. What was delivered? Stay near the mic. Stay near the mic. Yep, sorry.
Is there a cursor you can just move around?
All right, let's see if this will... I got a mouse here. Okay, so globally now, the average delivery rate in megabits per second is 1.5 megs. This is averaged over, I believe, Q4 of last year. And we publish, actually, these statistics in much greater detail, and that's in that blue report that's sitting on your desk. And that has the report from Q4. We now have one online that's the Q1 report, and we make this public so that you can see how fast average bandwidth or throughput is to end users. And then you see it broken up down by continent. Now, here I'm going to give you a little bit finer grain view. The green is showing in the 3 major continents the fraction of IPs that we deliver to at over 5 megabits a second. So this might be classified today as high broadband. It's good enough to get DVD quality live. People call it HD, but HD would really be, Blu-ray would be much higher. And the yellow is the percentage of IPs that we see between 2 and 5 meg. So maybe we'd call that today broadband. That's at least TV quality. Then the orange slice is those between 256K and 2 megabits a second. At the upper end of that, you can get TV quality. At the lower end, it's pretty lousy. You're really not looking at good video. And then there's the small red slice that's below 256K. So we've seen a rapid increase in improvement of achievable last mile bandwidth. So you may have a 30 meg pipe, but we'll count you here much lower if we can't deliver to you at 30 megs. And that includes all the things in the internet. Yeah.
These numbers seem higher than I would have expected, and I'm wondering if you could explain how you measure it, and
yes,
also how the numbers might change if it was weighted by traffic volume as opposed to IP. For example, like what's the median here, and also how much it changes weekday versus weekend, where people might have slower connections on weekends because they're at home.
Right. I think if we weighted it by bit traffic, the numbers would skew more towards a higher throughput rate because we're measuring the throughputs based on large file delivery. Think of it as a movie, a video, or a big software download. And, of course, that would dominate the total. So maybe it would be the same. I don't see that skewing it, making it less to show less throughput available to end users. We measure it by statistics on our servers. It says we delivered a 100 kilobyte file in this much time, and that's reported in a log line to this IP address. And then what we look at is for an IP address, what is the maximum delivery rate from the sample we took? Now, it is true that if we had one sample point for this IP address that said it was very high throughput, 5 meg, and one that said it was lower, 1 meg, we'll report the 5 meg because that's what we achieved. So that may be accounting for some of your intuition there. So we know that IP, we can deliver to it 5 meg because we did. We delivered a big file to it at that speed. In terms of weekend versus daytime, I don't know the answer to that. That's an interesting question.
A quick question.
Yeah.
Is this using the Akamai infrastructure or is it the Big I internet?
No, it's both. It's using the Akamai infrastructure. The question is this using Akamai or the internet to make the measurement? And the answer is both. This is an Akamai server, which is generally sitting very close to the end user. So we're not going through San Francisco to Tokyo here. If we have an IP address in Tokyo, odds are very good the Akamai server is in Tokyo in that ISP. In fact, that's true around the world. So you wouldn't see this performance if you were delivering big files from a few data centers. You'd see much worse performance because delivery rate very much slows down as you go across longer distances in the internet. Yeah.
So, the microphone. Good, thank you. So we're always told that in North America we're behind in terms of broadband deployment. Is this because a lot of this is from people at work? Or are we not as far behind as we're told?
Well, I can't tell you for sure this is because people at work. I think it's believed that there's much higher bandwidth at work than in the home. So there's a lot of broadband moving into the homes now. We have not segmented these IPs by home or work, and I don't think we have the ability to do that. But as you can see, there's certain countries. In fact, if you look at that report, you'll see Korea, huge, high broadband rates. And you can see that in the report based on the IPs. In fact, let me just show one last stat here. This is showing how many IPs per capita. So if you took the population in the United States, you can now multiply by 0.35, and you would see how many IPs we saw and did this measurement against in North America. And it gives you a feel, of course, North America has more IPs per capita than, say, Asia does. That gives you some way of maybe putting this into context. The bottom line here is, though, that the last mile connectivity is pretty good, and it is reachable if you're serving from nearby. You can get today good broadband to at least half of the IPs today, which would loosely correlate to half the end users.
So I'm back. I'm Stephen Stuart, and for my brief introduction, I've started a few networking groups here at Google. My current internal title is Iron Chef Networking, which I like because it sounds a lot better than Loose Cannon.
Well, that's a pretty good description.
But I currently work in Production NetOps, which is the group that builds and operates our network that faces the capital I Internet. I'm going to talk about a project that we recently launched called Measurement Lab. It is our attempt to help. So I'll make a brash statement. It's our attempt to help repair the damage that has happened in the relationship between academia and industry. There are a lot of very good relationships in that that can be characterized as academia and industry working together. But we found that in the internet space, in the capital I measurement of the internet space, there's a lot of progress to be made, mainly in the area of helping academic tools get industry-style deployment in the capital I Internet. We like a lot of the tools individually, but when they are deployed at scale, they have problems reaching users, so on and so forth. So who is it? It's this set of folks. Why? And again, not to date myself, but we used to call, I guess what's now called slash dotting. We used to call it surviving a flash crowd. And so we would like to have academic tools deployed in infrastructure that is capable of surviving flash crowds. The focus of MLab is active measurement of infrastructure. This is in contrast to the kind of numbers that we actually collect as that Google would collect, or that Akamai would collect as the serving end of serving infrastructure. Here we want researchers to have the tools to develop a detailed view of what happens when they interact with a user on the internet. And ideally, if we can help them with the marketing with lots of users on the internet. Probably the best known tool on this in terms of public notoriety is Glassnode, which was the tool that was used to determine whether Comcast was interfering with BitTorrent. And they got slash-dotted with vigor once people figured out that they could use it to determine whether Comcast was interfering with BitTorrent. Our goal here is network transparency. We are trying to bring data to debates that haven't had a lot of data. All of the discussion of network neutrality on Capitol Hill, for instance, seems to be conducted without the benefit of data. So if you want to know what it is, think Planet Lab. It is run just like a Planet Lab install would be run, except we have a minimum baseline for what kind of machines and what kind of connectivity are deployed. We have 3 fairly modern servers, multi-core, decent amount of memory, all connected by gigabit to the internet, so that we can do the best that we can to ensure that the server end of the measurement platform is not the bottleneck in taking any measurements. And that's our current deployment scorecard. We just brought our 5th North American node up last night, so I hastily went in and corrected the slides. So I'm going to present some results from MLab. It's important to note that these are the results of the researchers who are using this platform as a means to make their tools visible to end users. The MLab would not be without these folks and the others that we hope to recruit to turn this into a first-class clearinghouse for running tools that would collect active measurement data from users in the public internet. NDT, brief show of hands if you're familiar with it. well, goodness, you should all go and test your home broadband right now. This is more sophisticated than the speed test stuff that you would find from some of the broadband providers who, they want to, basically just, throw up a little speedometer to help you decide to use their broadband connectivity rather than someone else's. There's a lot of what we hope is helpful configuration advice that goes along with conducting this test to help educate users on what it means to, for instance, tune buffers, what it means to get in and tune TCP. We actually, in this tool, try to detect and advise on problems like duplex mismatches. It's proposed that a non-trivial amount of internet performance woes are due to duplex mismatches in home networks that people have no idea how to detect or correct. This is one of the summary views of what NDT tries to tell us about what the internet looks like. Now, it's important to remember that all these results are from the people who the set of people who self-select to use this test. And we see that we have a lot of cable DSL users electing to come use this, and we think, but can't prove obviously, that they might be attracted by Glassnost to determine if their BitTorrent is being blocked. But because we have all these tools in one place, they're encouraged to use other tools. So we're hoping to get a lot of cross-pollination from having all these collected in one place, where users can self-select to do a variety of tests rather than just the one that attracted them to the site to begin with. So here, for the people who used NDT, the bottleneck link in most cases was determined to be a cable modem. One of the other things that we collect, we integrated the Web 100 kernel patches into the Planet Lab OS in order to be able to collect Web 100 exit statistics from TCP sessions, and to be able to poll the kernel for detailed information of the performance of TCP during the session. So during this NDT 10-second test, we polled the congestion window versus time at 5 millisecond increments. And so what we see here is slow start to the user's 64K buffer, and then we start to see events that bring the congestion window way down. Here you see slow start trying to bring it back up until you reach the threshold where congestion avoidance takes over. And we believe that the differing size of these peaks in the sawtooth indicates differing rates of cross traffic interfering with this particular TCP session. We can stack that up against a TCP dump and see where retransmits indicate that we've lost, so on and so forth. So, as we collect more and more of this data, we expect that it's going to be, I'll make the rash statement, a treasure trove of data into the performance of TCP in real live end user broadband networks. Glassnost, as mentioned, was developed to determine whether BitTorrent was being manipulated. What these folks found was that 25% of users who came to test had their service degraded. Glassnost is also able to compare BitTorrent protocol transfers with reference flows that are not BitTorrent. And what they found was that 60% of flows that have differentiated performance, 60% of them were throttled to 0.5, the throughput of reference flows, and 40% of them were reduced to 0.2 of the throughput of a reference flow. And there's a lot of detail by ISP, by continent, by slicing and dicing the results that's coming up in their SOSP paper. Pathload 2 is one of our newer tools that focuses on measuring available bandwidth. This is different from looking at TCP and making a determination based on a large TCP flow like a lot of speed tests do. This is actually using basically raw protocol datagrams to try to assess how much available bandwidth there is in a home network connection. And they're starting to come in with some results that indicate what kind of throughput you see. So these are results per ISP. This one here, I know it's an eye chart, even for me. This red one here is Telecom Italia. And you can see their results are all kind of clustered below 15 megabits per second. One of the things that we're very much looking forward to doing is correlating these results with other tools to determine what was TCP throughput in a test that's reasonably adjacent to a path load test. And they've got downstream and upstream is clearly less. You might this is Comcast here this time. So you might infer that this might be with the DOCSIS 3 rollout, people might be coming to test. DiffPro, this is one of the ones that we're kind of most excited to get going. This tests for discrimination, looking at flows of different types. Getting back to the is ICMP punished or elevated in priority. These are tools to try to detect what kind of policies are subjected, or packets are being subjected to policies that cause the flows to be buffered or policed or what have you. Some of their preliminary results are one of the examples of bad behavior in the network neutrality debate is whether Skype and Vonage would be punished relative to the native VoIP offering of a provider. And one of the preliminary results here is that that's not happening in the internet today. They have got results that show that Comcast residential traffic shaping was detected, but per customer, not per application. So we're seeing the behavior of policing or shaping across all flows associated with a residential network customer, but not targeting specific applications, at least not yet. And that is the end of my presentation. Questions or?
One obvious one from a standards wonk. Do you intend to input this into an appropriate standards for it? And I'm thinking particularly, at least in a lot of the ones I play with, particularly under the NGN rubric, you've got a lot of people who are basically developing specifications that sort of work against you. So having these available for agencies that look at things like net neutrality types of discrimination might be a good thing. And so are you considering that?
And so you tell me if I've answered the question. We are planning on having, one of the conditions for deploying a tool in this network in MLab is that the tool is open sourced, and that all the data are made available eventually. We prefer that the data are made available kind of as it's measured, or as it's collected. For researchers who have concerns about access to the data before they've written a paper, we take a page from our brethren in astronomy, because this is kind of like a telescope, right? A telescope that points up at the sky is a big shared resource that people book time on, and this isn't terribly different. The goal, though, is to get all of the data into the hands of researchers, whether they were the ones who conceived of the experiment and collected the data or not, so that post-collection analysis can be done with a different eye toward answering different questions than those that were necessarily the questions when the data were collected. And in fact, we're trying to turn this into a more general platform that's constantly throwing off data, rather than the data that's just conceived of a single experiment. But as far as getting into the hands of standards bodies and whatnot, it's really the researchers that drive that. We want them to take these results to standards bodies and to referee journals and whatnot.
Regulatory agencies could drive it too.
Yeah, well, the comment is that regulatory agencies could drive it too, and we have one of the participants in MLab is New America Foundation, whose Open Technology Institute is very much interested in acting as a bridge between the researchers and the regulatory agencies to, as I mentioned in the beginning, bring data to debates that have not had data before. And in fact, we have some of these results that I just showed from the researchers have been taken to regulatory agencies to try to bring data to these debates. Yeah. Yes, one last question, and then Greg can come up and.
So for the no discrimination of Skype vonage, have you tried to differentiate between video and audio traffic to see if there is actually discrimination against video traffic?
So we're putting the kind of finishing touches on a call for tools, and right now we have tools on the site that are very much focused on TCP as the delivery mechanism for data, right? And they slice and dice the TCP protocol to find out its performance. We would like to, if you will, commission tools that would do the same for RTSP as a video delivery protocol, for SIP as a means of doing VoIP. Some of the challenges are, how do you bridge this platform with the PSTN, for example? Can we sign up for an 800 number that people can call from the PSTN to interact with a server that, I don't know, plays some pre-recorded message, asks the user to input some DTMF tones in order to assess the performance of the VoIP half of the call. As an example, for people who are trying to develop products in that space, that data might be really useful. Then, once you've done that, how do you scale so that you can have, 5,800 numbers from different providers and provide the same service to collect the same data? But that's, that kind of operation at scale is something that the research community hasn't really had access to, and we're trying to expand their minds with regard to what tools they could deploy, knowing that they have a platform out there that's POPs deployed worldwide, minimum of a gigabit of connectivity, to do with as they please, et cetera, et cetera. Greg.
I'm an old friend of Vince. FOV. I've been doing stuff in networks since before the internet.
Since before they were networks.
Yeah, right. So it's my, I'm honored to say a few words to this group about what my team and I are doing. This is just a brief slice of what we're doing. I hope you might find it interesting. I apologize for not putting up some microsecond resolution graphs of large-scale Google traffic. I will do that at some point, but I just didn't have anything appropriately sanitized for today. So I hope that the snapshot you're going to get will actually be useful. BURP is our cute little name for burst packet analysis. I think in Tom's graph, he mentioned at one point some links that had 6% packet drop. 6% packet drop makes people scream around here, and so does 1%. They'd like to see 0, but nobody's going to pay for that. So we live with on a tight balancing act between buffer size, the cost of gear, the amount of traffic we can send through the links, and acceptable packet drop. You drop a packet, you lose a transaction, or latency goes up, et cetera, et cetera. So why work on this? Well, everyone is sensitive to packet drop. Packet drops seem to be caused by bursts. NetOps says to everyone, burstiness is bad, please make it smooth. Our internal enterprise congestion seems to be caused by microbursts. These are bursts whose duration is shorter than an RTT, so the congestion avoidance mechanisms don't really see them in real time and can't. Of course, you never can put on buffers that are big enough to handle all of the traffic we're trying to put through. So what is the right size for a buffer that you can afford that will help you manage the bursts? Well, nobody really knows because until we started building special purpose snippers, you couldn't get a picture of one of these things. And the measurements that you see at the end nodes don't tell you what's happening in the core of the network. So there was, when we started some of these projects, there was this feeling that if you could just do traffic smoothing on everything to smooth everything out, that life would be wonderful. So how much smoothness do you need? And if you had ultimate smooth traffic, would it help? So I decided to learn a little bit more about that. And this takes the form of trying to use statistical means to be able to predict packet drop as a function of the traffic that's being put on the link and the buffer size. That's where it started. That's not where it ends, but that's what we're doing. So in order to do that, here's an overview of the procedure. First, we get time series from applications, from an individual application as well as from an aggregate of many, many thousands of applications running over an aggregation link. And for the next few slides, I'm going to show two applications that we measured. Both are trying to do a constant packet rate file transfers, very long duration, like a file transfer that takes a few days, using two methods. The XYZ, that's not its real name, but the XYZ method was a bulk UDP transfer app where the rate control is being done out of the application, not the kernel or the protocol stack. The other one, QDisk. QDisk is the Linux name for the queuing line discipline that goes in the kernel, and it has a traffic shaper. And there's another application that we measured, which is competitive in some sense with XYZ. So we looked at both of those, trying to do the same thing but using different means. What do? We take a look at the time series and we extract the PMF from it, which gives us the burst statistics, general traffic statistics. Then we spent quite a few months working on change point detection. Change point detection is a big deal if you're a statistician. What it means is if you're looking at traffic flow, there's some distribution that describes the packet arrival rate and the burst. Well, what is it? And has it changed in the last few milliseconds? If you can determine that it's changed, then you've perfected the art of change point detection. That's the technical word for that. So we look at our time series, we try to determine the underlying distribution, but of course there's more than one underlying distribution. So we work real hard on figuring out which distribution applied during which segment of time and where the change points are. So we've gotten pretty good at that. We've gone through hundreds of methods, right? So I put up a little graph that shows where the change points was. It doesn't tell you the other 99 methods that didn't really work so well. So we produced the distributions, and along the way, we've noticed that these change point detection methods are actually pretty good for anomaly detection. So for instance, we have a lot of dashboards and monitors within Google that are trying to observe when something goes wrong. And they'll get lots of time series from a lot of different sources in the network, SNMP, logs, all kinds of stuff. There's quite a large number of time series sources. And of course, they all have underlying distributions. And if you can detect a change point, you may be well on your way to saying, hey, something's gone wrong. And so the team is actually working on that with some pretty good results. Having extracted the distributions, we analyze them. So one of the ideas was this. Let's suppose I know that a file server inside Google has 10 to 15,000 active connections. And I want to simulate that or try to figure out what the burst activity is of all of those active connections with respect to a switch buffer someplace. Well, what we can do is, what we decided to try to do is to get a traffic distribution from one client, right? Measure it. And then use a convolution technique to figure out what the distribution is for 10,000 clients, however many you want. And that seems to work. So if I want to figure out what the traffic and the burst dynamics are for an aggregation link that's got a few million connections on it. Well, I can take samples from different single servers, say within Google or any place, and I can use this convolution technique to figure out what the aggregate cumulative distribution is when I stick a million of them together. And if I do that, then this last technique, the modeling technique, can help us answer some questions about packet drop with respect to a certain size buffer. So that's what this is all about. So I'll show you a few things that we were able to do. We took the two applications that I already described. We extracted the distributions, and initially we use a closed form solution for what is the probability of an overflow during the next time window. Our time windows were 1 millisecond. So for as a function of buffer size. Now, that's the probability within the next time window if you were starting from an empty buffer, all right? So this was not particularly useful, and I gave this presentation. Everybody said, well, what's the packet drop rate per second, and yada, yada, yada. Well, the closed form solutions we were using don't yield that answer, and most people would then do a simulation. And we wanted to try to find some technique that would give us the answer without running a simulation, right? So that's what motivated the development of the state space model. So first I'll show you where we started, and then I'll explain how the state space model works, and then I'll have to stop. So here's some pictures of the raw data from the two apps. This particular one, you can see that it plateaus. It runs for a period of time, fairly constant, although it's bursty within its constantness. There ought to be a word for that. And then it changes. So what it's really doing, this server that we're measuring is constantly changing the number of flows that it's running periodically. And so what you're seeing is the server changing its mind and trying to maintain a constant packet rate during each segment of time. And so the green blip over there is highlighted in the next slide. It's a close-up of what was happening right around the green bar for this application. And you can see that it's all over the place, or it appears to be all over the place. Well, actually, it is all over the place. But compared to the next application, it's actually pretty good. The top one is XYZ. That's the UDP constant burst rate, bit rate in user space. The other one, QDIS, this is how the Linux kernel implements constant packet rate shaping. Because of the fact that it really likes to burst, it's really, the best it can do is take the bursts and spread them out over time. Those peaks are the sort of natural 64 kilobyte burst that's inherent in the stack plus the driver. And what this thing is doing is controlling how many of those blobs per second it puts out. So if what you were really trying to do is to minimize the bursts that you see when you get 1,000 of guys doing the QDISC all coming together, it's not going to look too good because the probability that several of them tried to do some of these bursts at the same time is pretty good, right? So when you scale things up, these bursts get worse and worse and worse. That is, you can read that off on the right, where the standard deviation of the XYZ is much less than the standard deviation for the other one. Now I'm going to zip through another couple of graphs because the results are really sort of obvious. The graphs really show that under the constraints of the closed form analysis that we did based on these distributions, the top guy is much less likely to overflow its buffers during the same time window as the second one. That's a fairly obvious result, but there it is. This is the point. If your traffic has high variance compared to low variance, and you want to minimize the drop rate, then you have to run at a lower utilization. And so these are wonderful hand-drawn graphs. There's some time going backwards effects in the red thing that some people get a giggle out of. But this is a notional diagram. So if you can solve the problems that I've been outlining here, you can then determine where you want to adjust the utilization knob on your link if you want to control the packet drop. Well, if you're getting ridiculously high, deep bursts, and you want to keep the packet drop rate down very, very low, obviously you must have a very low utilization. And so the VP of operations will look at the utilization figures and say, hey, you're running this thing at 20%, and I'm paying for it. I don't want to do that. To figure out how to run it at 90%. Everybody wants you to run a very high utilization, and then these bursts just kill you. And the other thing I can mention, because I didn't have a graph that was suitable to show, is that I haven't said anything yet about QoS. What happens in QoS is the high priority traffic, which is bursty, always goes through. The low priority traffic is clipped to some limit. And when the high priority traffic comes in, it's the best effort traffic that gets slammed because we don't drop packets for the high priority traffic. So bursts on the high priority traffic cause the best effort traffic to look terrible. And so you can think of this as collateral damage. And it's pretty much invisible to well, most of the tools and most of the protocol stacks. That is the problem. And of course, as I already said, it's unacceptable to run the overall utilization on the link low enough so that this doesn't happen. That's the problem. Oh, I should also say that I've got my own ideas of what should be done about this. I'm not talking about those today, but you can probably sense that working on some very careful measurement tools and gathering data like this is intended to support the engineering decisions associated with what we do going forward in terms of what's the buffer size, what hardware to buy, what to do in the protocol stacks. All this stuff is related. And it's fun to work on. These are, I won't spend any time on these. This simply showed that the XYZ method was better than the other method. If someone really wants to look at the charts, we can do this. But the results were, for this, they showed that, there was a difference. So how to do better than this to actually get packet drop rates. Here's a simple little experiment. You have A and B sending to C. They're going through a switch. They're running a test program that we have around that simulates the RPC traffic. So they're sending random 1 megabyte RPC messages to C. And the load is set so that it's going to overflow the switch, right? And I haven't drawn the measurement equipment, but all the links are tapped. So we have a trace of packets going into the switch and a trace of packets coming out of the switch. And this is just absolutely hilarious to me, right? Because you detect congestion when you see the packet go in the switch but not come out. Switch as mouse packet trap. And so we've done this on a fairly large scale so that for some of the switches inside of our infrastructure, we can do this for all of the links going in and out of a switch, not just A, B, and C, right? And with that and microsecond or less than 1 microsecond resolution data, you can really start to get a good picture, a real picture of what's going on with these microbursts. So anyway, we do that, and we've developed the software to look at this stuff that identifies the dropped packets, figures out the drop packet rate, and then we extract the packet distributions, as I was illustrating on the previous few slides, for the inputs and the outputs and the drops at pretty good resolution. So this shows, for this nearly trivial case, the top thing is the distributions for the two flows. The middle trace is the distribution of the aggregate flow, the sum of the two. And I'm showing the measured aggregate distribution as well as what we computed it would be using the convolution technique. And because the things are overlapping each other, it's hard to see what the differences is. So in the bottom, we're showing what the error term is between aggregated and the computed distribution. And it's quite good. The mathematical theory is quite sound, so we think this is going to scale up to a gazillion flows, whatever we want. The beauty of it is that if you believe that the next thing I'm going to show you is worth it, this lets you synthesize the statistical properties of a nearly arbitrary combination of flows. Right? And so without running a simulation, this is really kind of sweet. So the way this works is we use some results from trellis coding theory to build a state space diagram where the states are labeled vertically S1 through S whatever it is. Each one of those states represents, you can think of it as number of packets in a buffer. So at the top, S0, it's empty. And at the bottom where it says overflow, that's an n plus first state we add to capture the statistics for when the thing is overflowed. So for each one of those states, you can read out directly from the distribution of that we've calculated according to the previous slides. You can read out how to compute the transition graphs. In other words, an arrow from the left-hand side to the right-hand side is the probability that if you're in that state, you're going to go to the next state on the right, which is either, more buffers or no change or a little bit less, and how many packets you might drop along that transition. This is also assuming a drain rate. So if no packets are coming in, we assume in the time period the drain rate are going out of the buffer. So the buffer is draining. That's how. So we're assuming that the buffers are drained at, some rate. Pick a number. Anyway, so once you do that, you can then do a lot of calculations with this. Oh, I should also say that the theory behind this assumes certain properties of the time series. One is stationarity, and the other one is that the random variables are independent, and that's really a problem. We're sort of like these distributions are not perfectly stationary, meaning that from one time sample to the next, the distribution may not be exactly right. And that's certainly true for this case where we only had 2 flows. We think that is less of an issue for thousands of flows, right? So that's one caveat. Second caveat is independent random variables. Well, if you think that there's a random variable describing the traffic dynamics for one flow, ask yourself, is it independent? Well, no, it's not, because we already talked about collateral damage, the fact that the TCP, slow start, and all these things can act in synchronization. There are all kinds of things that make them not perfectly independent. But for a large enough number of slows, they're independent enough so that this trellis state space diagram is approximately correct, right? In other words, good enough, right? After all, we're using Ethernet. We might as well use something like this because it's it's good enough, Flow control, what the heck, TCP will fix it. So, for this nearly trivial example, the red line at the bottom shows the measured packet drop rate, which was constant, and we were very pessimistic in predicting in the calculated packet drop rate. But we believe that for the size of this experiment, that this says we're sort of on the right track. So obviously, what we're doing is expanding this, acquiring more time series, especially on the really big links, scaling this up to millions of flows. I'm also interested in measuring something called packet dispersion. All of the TCP stacks in the world try to send out bursts of back-to-back packets. Well, that's what goes into the switch. What comes out? Are they still back-to-back when they come out or not? Well, there are many theories on that, as there are people that understand this problem. So I aim to make some pictures. We're trying to answer that. And I also mentioned that QoS is another destabilizing factor, especially if one of the things you're trying to do in the place where you get the most complaints are from the people that have the best effort traffic who are getting slammed by the other bursts, right? So the interaction with QoS is also important. And we also have links, very high bandwidth links with low utilization. In other words, only 60%, but they still get packet drops. And I had hoped that we would have some microsecond data to show on those today, but the equipment is still being set up. So we will publish that. In fact, there are some time series that we got on some servers. I did this a request from some researchers at the University of Barcelona, and they agreed to make those time series available to other people, and I think other people will be interested when they publish their paper. So when we get some more really high bandwidth voluminous data, we can make it available, for people to work out, because I think it shows up some issues with respect to QoS, microbursts, and congestion that I think are of interest to everyone, small, medium, and large. That's all I have. Thanks very much. There was a question. Oh, I thought everything was perfectly obvious.
Boy, that's a challenge. Really stellar stuff there. I'm blown away. I got distracted several epochs back in your talk.
Want me to go back?
No. Oh. When you talked about 80% versus 90-odd%,
yeah,
and people not wanting to pay for only 80% utilization, and it strikes me that we all have grown up. The whole industry has grown up with percent utilization as one metric, and then jitter and other things as other metrics. And it's that percent utilization on which you get sucked into saying, well, we're underutilizing, and therefore we got to try to raise that. And with the other statistics suffer. Let's see if I can frame this question right. And it's not only to you, but to anybody else who lives in there. Would it be possible to replace those particular dimensions with some other dimensions that aggregate or slice and dice the space better, so that it's quite evident that as you raise utilization, you're making some other aspect much poorer, raising the risk and so forth, so that we can change the vocabulary?
Well, this is a social engineering problem, not a technical problem. And the second part of my answer is that since I'm mostly studying Google internal enterprise traffic, there are things that we can do that don't really work on the internet. In particular, if I could show you some real traffic graphs, you'll see there's a diurnal pattern with peaks during the day, and there's weekly patterns and there's monthly patterns. All of these are detectable. So normally you see the best effort traffic. If this is the graph, right? Imagine the graph. And you break it out by QoS, you'll see best effort down here fairly constant, right? And then you see the diurnal load traffic going like this. Obviously what we could do, so the utilization is less during the trough than it is during the peak, right? So obviously what we really ought to be doing is raising the traffic shaping limit on the best effort traffic during the trough so it can go up and go down. And so then you increase the average utilization. Ta-da, right? Can't do that on the internet, right? Because you don't have that control, right? So I can do something with traffic utilization on our links with the $200,000, remember that, line cards, which you can't do on the internet. So that's a long way of saying I don't really have a good idea on what you can do for internet utilization. Third thing I would say comes from high performance computing. You want to make a parallel computer, you want to make it really go fast. It's not going to go fast all the time. You pay for a lot of idle machines so that when you hit the peak in the computation, they could all be running in parallel. That's what you pay for. You want a racing car, gets lousy mileage. And so some of the trade-off between not running at 100% utilization all the time is so that you can handle the peaks in the traffic, right? And so it seems to me that what one can do is try to fix it so the peaks can be spread out over say more links or alternate routes. You take some traffic during the peak times, you send it over routes that are not optimal, more hops, something like that, in order to be able to run the whole thing at a higher utilization, spread traffic around. But that requires dynamic adjustments to routes, okay, which will make our existing routing algorithms look simple. And of course, they're not simple. In other words, I think I can imagine things that can be done, gap filling, hole filling, et cetera, but I don't think it's going to be easy to do, especially with multi-vendor, multi-equipment, multi-ISP, all trying to do the same kind of thing. I think it would be tough. So the answer is, I got some ideas. I don't see how to make them work yet.
Thanks.
Mm-hmm. So we're way behind time. Unless anyone wants to close with a question or two, I think we need to take a break. So
ordinarily, we would have had all the panelists up here for more Q&A, but it's now 10:15 according to my Ronald McDonald watch, and we were trying to schedule a break for half an hour. Now I'd like to schedule a break for 15 minutes, honestly, and restart at 10:30. Part of the reason for trying to stay on schedule is that we have Eric Schmidt coming right after lunch, and it's really, really important for you to get back here from lunch to be here when Eric gets here at 1:15. Otherwise, I'll be in some jeopardy if the room is empty. So out of courtesy, I hope that you would come back. So let's take a break until 10:30, and we'll resume with the next panel. And let's thank this panel very, very much.